and Liz. Let me just say a few words. Liz McMahon, is that right?
McMahon, yeah,
McMahon.
close enough.
Is a Chapel Hill, North Carolina native, and earned her bachelor's degree from Mount Holyoke College in Massachusetts, and also an MS from the University of Michigan, and a PhD in the field of non-commutative rings in the University of North Carolina. She's a professor of the Department of Mathematics at Lafayette College. Her research interests include the fields of combinatorics, finite geometries, and Cayley graphs. She has written The Joy of Set, The Many Mathematical Dimensions of a Seemingly Simple Game, a book about how the game of set can help visualize properties of finite geometries. And she also had the pleasure of co-authoring that book with her husband, Gary Gordon, and her children, Rebecca and Hannah. She teaches workshops in calculus and has taught a course on gender and society, and works on increasing the success of underrepresented groups in mathematics. She has been recognized for this work by winning several teaching awards at Lafayette College, and also the Mathematical Association of America's Crawford Award for Distinguished Teaching of Mathematics. Beyond that, she's also an avid bicyclist, hiker, and rock climber. Liz, it's all yours.
Thank you. Now, what I do is I share my screen.
Yeah.
Where is the thing I want to share? That's the thing I want to share. Hi, so I'm Liz. I'm going to talk about the mathematics behind the card game set. If you don't know the game, don't worry. You'll be sorry, I hope, by the end of the talk. I would just like to point out I'm wearing my pie shirt. And my favorite thing about my pie shirt is the back, explaining that I am rational, irrational, but well-rounded. So I'm going to talk about this game, the card game set, and I meant to have it with me. I'm back. Here it is. Here's the game. So, the game of set is played with a special deck of cards. Here's the box. I can show you some of the cards. If you can see me, you can see some of the cards. And what you'll notice is the cards that you see have either 1, 2, or 3 symbols. They're red, purple, or green. They're empty, striped, or solid. There's a striped, there's empty, and I'll find a solid soon there. And they are ovals, diamonds, or squiggles. I've had people call them peanuts. They're squiggles. I'm sorry, you got to get with the program here. Now, a set is 3 cards where each attribute independently is all the same or all different. So that's what a set is. So let's do some look at some. I am, for some reason, it's not, well, I didn't want it to do that. I'm trying to, there we go. Here are some examples of some sets. So it is possible to have 3 of the attributes the same. The set at the top here, they're all red, they're all diamonds, and they're all 3s, but they differ in their shading. So that's a set. The next group of 3, they're all striped and they're all squiggles, but there's 1 of each color and there's 1 of each number. So that's a set. The next group of 3, they're all 2s, but they're different colors, different shadings, different shapes. That's a set. And the one at the bottom is the one that most people consider the hardest kind of set to find. Everything is different. 3 different numbers, 3 different colors, 3 different shadings, and 3 different shapes. So one thing that can help you as you're learning the game, when we were first learning the game as a family, we spent a lot of time going, is this a set? And you learn the mantra, number, color, shading, shape. If there's anything where you can say 2 of them are something, but 1 is not, then you don't have a set. For example, the 3 cards you see there are not a set because 2 are striped, but 1 is solid. That's not a set. So I have here, I really wish I had audience participation, but your job is to decide for each of these groups of 3, is it a set or isn't it? First one, the second one, the third one, the fourth one.
I'll play along.
Uh-huh.
I'd say the first one is a set.
Would you?
It's not a set. You have two
Oh,
times.
it's 2 diamonds. Sorry, you're right.
There you go. So, and it takes a while to learn this. So yes, 2 are diamonds, 1 isn't, so it's not a set. The next one?
It is a set.
The next one is indeed a set. They're all squiggles, they're all 2s, different color, different shading.
Right.
The next one?
Yes.
That's one of the hard ones. Everything is different, so that's a set. The last one?
No, because they're both of them, 2 of them have the same number.
2 of them are 2s and 1 is not. Exactly. So there's your answer. And so in our house, we will sometimes call that a set because you started to say set, but then you realize it isn't one. And so it's just missing one thing. All right. So the way you play the game, which we're never going to do in this talk, you lay 12 cards out on a table. Each player is looking for sets. The first one who finds it calls it, usually in a loud and obnoxious voice, and takes it. Those cards are then replaced and you keep looking for sets. It's not a turn-taking game, it's a speed game. If at some point in the game, all the players agree that they can't find any sets, it doesn't matter whether there are, if everybody agrees they can't find any, add 3 cards. If you find a set among the larger group of cards, take it, but don't add 3 cards. You want to play with 12 because the processing time with 15 cards is much longer than the processing time with 12 cards. And at the end, the winner is the person who took the most sets. Everything in the world ought to have its own fundamental theorem, and set is no different. The fundamental theorem of set says, if you take any 2 cards in the deck, there is a unique 3rd card that completes a set with them. So these 2 cards are both striped. So the 3rd card better be striped. There's a red and a purple, so the 3rd one better be green. So we have number 1, there's a 2 and a 3, so it better be a 1, number, color, shading, shape. And there's our card. And essentially that's the proof that the fundamental theorem of set is true. For any attribute, if they're the same, the 3rd must be 2. If they're different, the 3rd must be the one missing expression of that attribute. This is from www.setgame.com set puzzle. They do this every day. And in here, there are always 6 sets to be found. And usually I'd have everybody calling out sets, and we just won't, because we just won't. But anyway, you could go play today's set puzzle when we're done. What does set have to do with flourishing, which is the topic of our day today? There's a lot of very interesting mathematics in the game of set, including much unknown, a lot of open questions, and very interesting math. So as you play the game, just ask questions. Some questions are going to lead to interesting math, others lead to open questions. Some questions are pretty quick to answer, but that's okay too. All right, so here are some examples of questions. How many cards are there? Okay, I know it tells you on the box how many there are, but you can figure it out yourself. You have 3 choices for number, 3 for color, 3 for shading, and 3 for shape. So the answer is either 3 times 3 times 3 times 3 or 3 plus 3. No, it's 80. How many sets contain a given card? I picked out a card here. What's interesting, because there are 81 cards in the box, this card, once I have this, there are 80 cards that are left. If I choose any one of those cards, we've learned from the fundamental theorem, there's a unique card that completes a set. So I can put those 2 aside. With this card, there's a unique, they're all red. There's a unique card that completes the set. I can pair them all up. Since I had 80 cards left, there must be 40 sets containing a given card. How many sets are there? I'll leave that one to you. It'll appear later in the talk. Use the last answer and kind of work with it, because you can do that. On average, how many sets are there? This one takes more thought. So we're going to spend a little time thinking about this question. Suppose you couldn't answer it right away. What could you do? Well, one thing you could do is while you're playing, start the game with the 12 cards on the table. The first person who finds a set can call it, but shouldn't take it immediately. Try finding all the sets in that opening layout. That gives you a number. Every time you play, you can collect another number. You're doing a simulation. You can get a sense of that. I will just tell you there are 3 sets in here. It turns out this is not a legal puzzle of the day because there's only 3 sets instead of the 6 that the puzzle
May I
of the
slip
day.
in a quick question?
Yes.
Is that number well defined? Could there be certain choices you might make initially that might change the answer depending on what you choose?
So I'm talking about just how many sets. And so if a set uses the same, if one set uses a card, if you remove it, then you're in trouble. But if you don't remove it, it counts all the sets, including a card might appear in more than one set.
Ah,
And so that answer, yeah, the answer is it can vary. So there you go. I can't remember if there are any in here that are multiples. But anyway, there you go. We'll come back to this later too. So what do we think the guess? I'm now going to ask you to guess. What I would do if I were in person is I would have an applausometer, but I can't have you applaud. So I want you to just think what you think the answer is. In the first layout, on average, how many sets do you have? Less than 2, between 2 and 3, between 3 and 4, or more than 4? You're thinking. The answer is
Less than 2.
between 2 and 3. It's about 2.7848 sets on average, which tells you that 12 is a good number of cards to start with because you expect to see close to 3 sets. You expect that. All right. So we're still looking in the initial 12 cards. What's the minimum number of sets that you could have in 12 cards? People who played the game might know the answer to this one. Okay. So
Must be 0.
it must be 0. It must be 0. It is possible to have 12 cards that have no set in them. So yes, indeed, the minimum is 0. What about the maximum number of sets you could have in a 12 cards? 5 to 7, 8 to 10, 11 to 13, or 14 plus. We could poll the people who were in the Zoom room. People want to guess? At home, I hope you're yelling out a guess.
I'll say 5 to 7.
Anybody else want to guess? I'm not entirely hearing people yelling out answers. Too bad.
I'll say why not? Actually, I'm inclined to say 5 to 7 as well, but
5 to 7? All right. The answer is not 5 to 7. So if we were remembering the first talk, I can knock out 5 to 7. It's not that. The answer is 14. It turns out you can have 14 sets in 12 cards. If I remember, or if somebody remembers to ask me a little later, I can tell you how that happens, because there's a very special way that it happens. Ask a computer to lay out 12 cards 100 million times, because computers can do that for you. Here's what you get. 3.2% of the time, there are no sets at all. 14.5% of the time, there's 1. 26, 27, notice 2 and 3 are very close. And then 4, 5, 6, 7, 8, 9, 10, 11. It actually happened in 100 million times, several times it happened that there were 14 sets in the initial layout. You have to play a lot of set to see that, though. If you ever see that, buy a lottery ticket. You're very lucky. All right, so suppose there's a set in the first group of 12 and you remove that set and replace it by 3 more cards. Do you think the expected number of sets is going to go up? Is it going to go down, or will it stay the same? I hope everybody at home is thinking.
I'll say I think it goes down. It's just my gut feeling.
Okay. Anybody else want to guess? And right now, it's perfectly fine you're guessing. It's a good thing to do unless you know the answer. The answer, indeed, it goes down. And here's why. Removing one set removes all of the sets that contain any one of those three cards. And that's 10% of the sets in the deck. So you've removed 10% of the sets, but you've only removed one card. So it's reasonable to expect that the number of sets would decrease. All right, so what happens is you continue to play. An interesting thing here, a computer simulation suggests that the expected number goes down. Oh, I didn't ask you what you think happens, but it turns out in the second layout, remember we were 2.78, it's down to 2.53, the expected number of sets. So it is dropped quite a bit. Where do you think the last layout of 12 cards, do you think the expected number of sets? So you've gone through the whole deck, and the whole deck is now on sets taken and on the table. In the last layout of 12 cards, do you think it's 1, between 1 and 2, or more than 2?
I'll say less than 1.
Less than 1, we have a guess. A second guess? We have a little disagreement. Duke it out. The answer is more than 2. And here is a lovely picture showing the computer simulation, showing this lovely graph, showing how the number of sets does decrease steadily, but it ends up more than 2.3 on average. You can see, by the way, here that big drop from the first layout to the second layout. Nobody knows the exact percentage. And it turns out, very interesting, it turns out if you do the computer simulation, you get different answers depending on what method you choose to remove the sets. So it's a complicated situation. So there you go. I'm going to talk about another kind of thing besides sets. Is there a relationship you can think of among the following cards, those 4 cards? There's something interesting going on with these 4 cards. If I reorganize them like this, what card completes that set? Going across the top. 1 empty purple squiggle, oval. What card completes the vertical set? It's the same card. So we call this in our house an interset because it's a pair of intersecting sets. So we call it an interset. So there it is. An interset is 4 cards that you can pair them so the same 5th card completes the set. Only one pairing can work. You cannot have 2 different ones. The interset pairing is unique. So you can't have a situation which you can draw for regular points in the plane. You can't have that with set. Doesn't work. All right. So how many intersets do you think you have on average in a random layout of 12 cards? Less than 2, between 2 and 3, between 3 and 4, and more than 4. So those of you who are watching this elsewhere, yell out an answer so the people around you can go, what are you yelling about?
Between 3 and 4.
We have a between 3 and 4 guess. Anybody else want to guess? All right, I'll tell you the answer. And what I will tell you before I tell you the answer is that when we figured this out, when we did this one, you can count exactly. We didn't believe it. Did not believe the answer. It's more than 4. So remember that 12 cards that I had before, it has 3 sets in it. These cards were the first 12 cards we laid out. And we started looking for intersets. We weren't finding a lot of them. And so Gary actually programmed the computer to count them all. There are 17 intersets in there. 2 cards, missing the 3rd, and 1 triple interset, meaning there's 1 card that would make 3 sets, 3 different pairs of cards. In case you don't believe me, these are the 17 cards that complete ordinary intersets and 1 purple solid squiggle, one purple solid squiggle. One solid purple squiggle makes a set with that one, and it take my word for it, it's in there. All right. Oh, I keep.
Can I ask you a quick question?
Yes, you may.
So I was wondering about the triples, and so you just answered it. So it is possible to have one card, one common card that completes 3 different sets. Is
Yes.
it possible to have one card that completes 4 different sets or not?
Within this, sure.
No, I mean within the whole. If you were to.
Oh yes.
Oh, okay.
Oh yes. Oh yes. We'll see this later. Actually, we'll
Okay.
we'll revisit this question. All right. So this was so surprising that we actually, Gary had to program the computer to actually count the intersets because we just didn't believe it, but now we do. So there you go. Here's the comparison. There are 1,080 sets in the entire deck, so you can check that out. On average, you expect to see 2.7848 sets in a random collection of 12. There are 63,180 intersets in the deck. On average, you expect to see 18.8 in a random collection of 12 cards. It's just, this was a true surprise for us. Next, you can ask questions about looking. Remember, early on, I showed you all attributes different, 3 different, 1 the same, 2 different, 2 the same, 1 different, 3 the same. Those are all possible kinds of sets. Which is the most common that you might have in the deck? You might think it's not the bottom one. I should not touch the mouse because it advances things. That's the answer. Sorry. I meant to give you time to think. So 3 different, 1 the same is the most common. And those are not approximations. Those are exact. It's really lovely. All right. So you play your game and you go down to the end. And when you get down to the final layout of 12, you're allowed to continue removing sets. Remember, we expect on average to see 2.3 sets. So you might find 1, you might take 1, you might take 2, who knows? How frequently do you end the game with the various numbers of cards? A computer simulation, once again, we use a computer simulation to answer this. You can clear the entire deck about 1.2% of the time. 3 cards never happen. I'll talk about that in a minute, but that's interesting. 6 cards, 9 cards, notice those 2 are very close to each other. 12 cards happens, 15 cards happens. I've had it happen. I've never, I think, had 18 cards left. Pretty rare. So interestingly, one of these questions, how often can you clear the deck? You can find it all over the internet, but nobody's counted this exactly. So all we have are available to us are computer simulations to answer these questions. So why did the game never end with 3 cards on the table? Math time. Each expression for an attribute is on 27 cards. So there's 27 reds, 27 purples, 27 greens. If you assign the 3 expressions, the numbers 1, 2, 3, red is 1, purple 2, green is 3, do it arbitrarily, then the sum for that attribute over the whole deck is a multiple of 3. 27 times, there it is. The sum of that attribute for a set is a multiple of 3 also. Red, 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 purple, 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 green, 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 or 1 of each. So if you have exactly 3 cards left on the table and no one has made a mistake, then the only way those 3 cards can add up to 0, add up to a multiple of 3, is if they're all the same or they're all different. So if you trust the people you're playing with and you're down to 6 cards and you spot a set, you should yell, set, set, because there should be 2 sets on the table. That's only if you trust your fellow players. Remember, there was never 21 cards left at the end. I'll go back. 18 cards was the most we saw. Here, the maximum possible number of cards without a set is 20. This is what's called in geometry a maximal cap. Terence Tao believes that the general problem of the size of a maximal cap is one of the most interesting open questions in mathematics. So I believe him. So there you go. It's an interesting question. Here's an example. Say?
A quick question. Is there a penalty for calling out set and there isn't one?
The rules that come with the game say yes. My family says no. We believe that we all make mistakes. And so actually we don't even call set anymore. We just take them. So but if you play by the set game rules, then yes, there's a penalty for that. But we're not so mean. So you should decide what rules you play by when you're playing. So if you look carefully at these 20 cards, you will discover there's no sets in there. It's 20 cards. There's some interesting structure going on here. In particular, I've chosen a card. Pick any card in that group of 20, whichever card in there is your favorite, and complete the set with that card. What do you discover? Whatever card you pick, the card that makes a set with one solid purple squiggle is in there. So this is actually 10 sets with the card on the right. That is the actual structure every maximal cap in this. It's a geometry. We're going to get to that soon. This is a geometry, and that's the structure of the maximal cap in that geometry. It's 10 sets with a single card, and then remove that card. And there's a lot of other hidden structure. I've done a lot of research with students on this question. Here's what's truly amazing. The top is that first one that I showed you. There's another collection of 20 cards with no set, where each card, it's 10 sets through that point, and another and another. That's all of the cards in the deck. So all of the cards in the deck here are making, I can partition the deck into 4 disjoint maximal caps with that one extra card. This fact was discovered after I gave a talk in England, and one of the attendees of the talk figured this out. And I have now spent several years, more than 10 years, working on this question of what's the geometric structure of these partitions. Very interesting questions. Don't have time to tell you about it. We're going to talk about the geometry of the game. So we're going to look more closely at it. Remember, 2 cards uniquely determine a set. I've got 2 pairs of 2 cards. So going horizontally, you can complete the set yourself. Done. And there we go. 2 cards determine a set. Doesn't that sound like 2 points determine a line? And the answer is yes, it does. This was one of the things that was so lovely about all of the talks today. I kept hearing things that I was going to talk about in my talk. So somebody mentioned, 2 points determine a line, that sort of thing. We're going to look at the geometry. This is a well-known geometry. It's been studied a lot. To my way of thinking, the fact that there's an underlying geometry is what makes the game so interesting. So I'm going to start with a cute trick to show you what we're going to do. We're going to start, just take any 3 cards that don't make a set. We're going to pair them up and complete the set. So for example, 2 empty red squiggles and 3 striped purple diamonds. What card completes the set for those? Everything's different, so the third is going to be all different. It's one solid green oval. Now take the next pair and complete the set. There it is. Take the last 2 and complete the set. And we get 3 new cards. Let's do it again. Okay, well, we could go through it. I'm just going to give you the answer. And you can see that this card completes a set with those 2. These 2 complete that set, and these 2, it's that one. What happens if you try to do it again? Well, let's look at these 2 cards. We have 3 solid red diamonds, and we have 1 empty purple oval. So we need 2 striped green squiggles. Do you notice something interesting here? The card that we need is sitting up there. What about these 2? One, by the way, if you're colorblind, I really apologize, because this is not going to be as much fun. The card in the upper left completes the set with those 2, and the card in the middle completes that set.
Also, the columns are sets too, correct?
I'm sorry?
Are the columns also sets?
Yes, they are. Yes, they are. There are a lot of sets in here if you look at these cards. So as long as you start with 3 cards that aren't a set, this process will always end with 9 cards. Take any pair of them, the card that makes a set is there. So we say the collection is closed under taking sets. There are 9 cards. This is an example of how knowing mathematics in the game can enhance your appreciation of the game. I'm going to rearrange the cards to sort of gather things together in a nice way. There are lots of sets. Can you figure out how many sets you can find in there? I'll give you some time on this one because it takes a little bit of time to find all those sets.
I'll say 8.
There are more than 8.
Are there 10?
There are more than 10. They're still there. Here's a schematic to help you.
Yeah.
Notice the horizontal collections of cards, those are sets. The vertical ones are sets. You have the diagonal, but you also have what I think of as a twisted diagonal, these two and that one. And you have another twisted diagonal, those two and that one. You have another diagonal, another twisted diagonal, and another twisted diagonal.
So is it 12 then?
It's 12, exactly. There are 12 sets. So we call this a plane in this geometry, okay? So there's a plane. There's an easy plane, all the green, solid green cards laid out nicely. And notice that the 12 sets occupy the same positions in the grid. You could actually take the axioms for this geometry and you could show that that's the way it has to look. It has to look like that. If you know that any 2 points determine a line and every line has 3 points on it. This is, by the way, an unusual geometry for many of us because it's a finite geometry. Every line has only 3 points on it. But the sets are in the same place. So, well, we had all the green ones. Let's add in the purple ones and add in the red ones. Where are the sets? The sets could be in the same places as a set in one of the 3 planes. That's a set, for example. If you also look at all of the middle cards, that's a set. The third way you can find a set is when you there's one card in each plane, and when you superimpose them, they're in the same places. So upper left, middle, 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 lower right, that's a set. So one way to see this is here's a little schematic. So these 3, sure, that's a set. The green ones are all the 1 diamonds. And the blue that's one of our twisted diagonals, but let's see. It's 2 solid green squiggles, 1 solid purple oval, 3 solid red diamonds. That is indeed a set. So there you go. This is where the sets are. So you can do this with your own plane if you've learned to make a plane. With one more card, you can finish everything. And the sets are in the same places as they were in the previous picture. The thing to notice is you're still following the all the same or all different. All the same row or 1 in each row. All the same column or 1 in each column, etc. So let's look at the 3 we had before. These 3 are those 3. That is surely a set. The upper left, that's a set. And the blues. So 3 green empty ovals, 1 red empty oval, and there you go, 2 purple empty ovals. So those are all sets. Isn't that wonderful? This is really beautiful. There's a lot of, this is just beautiful. If you actually, instead of having the planes side by side, if you stack them up, you can really see the dimensionality of this. This is a 3-dimensional configuration. All right, we could do this again, and we will. This is all of the cards in the deck. And this is just lovely. But we've got the same situation as before, except this time you take 3 planes in the same position as a line was in the original configuration. So I could take this plane, and this plane, and then look at the same spots or look at what is superimposed, the whole 9 yards. I have this up in my office. I end up spending a lot of time just looking at it because it's so pretty. I actually bought 3 decks of cards and I colored the backgrounds, and you can do this with 5 attribute set. It is a lot of cards, 243 cards. I think that I have played 5 attribute set all the way through 3 times in my life with all of those cards. At the end, I always have a terrible headache. So I don't recommend it unless you're that obsessed with set. And I am, so I do it. All right. I do want to tell you about another fun thing. And this is, in our house, we don't actually keep track of who wins the original game because it's always my younger daughter. If she's not home, it's my older daughter. If neither of them are home, it's me. And then if Gary plays by himself, he wins. And he knows this and he freely admits it. If you remove a card at the beginning of the game and put it aside face down, don't look at it and play the whole game, you can determine the missing card from the cards left on the table at the end. We call this the end game. So here are 8 cards because I should have had 9 cards left, but I hid a card away. Here's how you determine the hidden card. We're going to start removing sets, but they're not really sets, but they're pretend sets, considering only 1 attribute at a time. So if you have number sets, the blue cards are a 1, 2, 3. That's a number set. The green starred cards are 3, 3, 3. That's a number set. I know it's not a set, but it is a number set. What's left is 2 cards with 2 attributes. So the missing card has to have 2 attributes. What's interesting is it doesn't matter how you make the number sets. You could have chosen 2, 2, 2, 3, 3, 3. You're left with a 1 and a 3. That means the missing card has 2 attributes. So you continue. So we've done number. Let's do color. Purple, purple, purple is a set. Red, green, red, purple is a set. We're left with red and green. It's purple. What about shading? Can someone think about shading? Do you see some shading sets? I'm trying to see if there's a chat. I can't see the chat. So can someone look to see? Are people making a conjecture about the shading? That's a shading set. And that's a shading set. So it's those 2. So it is striped. So we have, the hardest part of this is remembering what you've already done. 1, purple, striped. What's the shape? Did I say 1? I meant 2. Right, we did 2. See, you don't remember. So I always end up chanting it to myself. 2 striped, purple, purple. There's oval, oval, oval. There's squiggle, squiggle, squiggle. What's left are 2 diamonds. It's diamonds. So it's 2 striped purple diamonds. But here's what's fun. Only about a third of the time will this work, computer simulation tells us. Oh, the question is, are there 2 cards on the table that make a set with 2 striped purple diamonds? And so, waiting. Somebody should be yelling, sad, sad, because why would I have given this to you if it didn't work? I can't do that. those 2 cards and the 2 striped purple diamonds. So that's what we now do. We just play to get to the end game. So it's actually a lovely check to see if anybody made a mistake in playing. If you're expecting a card and you flip the card over and it's the wrong card, that tells you somebody took something that wasn't a set. So if you were expecting that and you flip it over and you're expecting 2 striped purple ovals and you get 2 solid purple ovals, somebody made a mistake. But you know, even more than that, you know what the mistake was made in. The mistake had to have been made in the shading, because this is off by shading. There's so much fun stuff here. Here's one for you to try. I don't know how long I should wait. I don't know if I should do this. I don't know what to do, but I can give it to you. You can think about it. So I'm trying to decide how long to wait. I'm just okay, there it is. Yay, it worked. Okay, so but this is an example, yet another example of knowing something about the mathematics makes the game, to my way of thinking, it makes the game even more enjoyable. So we wrote a book. There's so much more set that I haven't told you about. There's modular arithmetic, there's probability, there's statistics, there's coding theory. You can make an error correcting code with set cards. It's just, there's so much beautiful mathematics in this game. And so we wrote a book to convince people such a thing. This is our family in the Poconos. So you can maybe spot me in the lower left and Gary in the lower right, and Rebecca's the upper left and Hannah is in the upper right. Rebecca's now a math teacher. Hannah was a math teacher. She's now working for the New York Department of Education in assessment. All right, I want to finish with a little story, and then there's time for questions if people have them. In 2006, the Set Game Company decided to have a national competition. And you could go to this Larson's Toys and Games, and there were prizes and free admission to the national set competition. So Hannah said, well, we have to go. And Hannah is the younger daughter. She's very good. So we went. So she and I went. So notice that the top 3 winners get free entry and registration. The top 3 winners were Hannah, me, and this guy named Grant, who'd driven down from Madison, Wisconsin. Well, that's Hannah and that's Grant, who'd driven down from Madison, Wisconsin in the finals. I was out early because I know how good my daughter is and I didn't have a shot. So I just let myself lose early so I could be done. So there's Grant is taking a set, and Hannah's taking a set, and I was trying not to be hovering mom. So I was watching and I thought he was beating her. And actually she did too. And in the final layout of 12 cards, remember we talked about the final layout of 12 cards? You usually ease up at that point. She did not. She found 2 sets in the final layout of 12 cards, and she beat Grant by 1 set. So she needed both of those. So she was named the national set champion. She's a set grandmaster. They've never had another contest. So as far as we know, she's the only set grandmaster in the universe. Yay!
The reigning champion.
That is her. And by the way, on the right there is Marcia Falco, her name. She's the inventor of the game. She was a population geneticist and stumbled onto this thing. So I'm now leaving you with a job. Your job is to play the game of set and just start asking questions and see how many of them you can answer. Thanks a lot. I'm done.
Thank you very much. That was great. Really enlightening and fun and not to mention colorful.
Very colorful, yes. And I really apologize. I have a deck that I've decorated for colorblind people. And actually the set company sells colorblind versions. I think it's like black and yellow and something else that colorblind people can play with. I just put symbols in the 2 symbols in these corners for the red ones, 2 symbols in these corners for the purple ones, to make it easier for colorblind people to spot the sets. So if anybody has any questions.
Yeah, I've got a couple of questions. This is
right.
really good. It's answered a lot of the questions I've played over the years. 2 of them. One is, if I were to put a bunch of dots on a piece of paper and show it to anyone, most people, and just say, find 3 dots that are in a line, most people would be able to do it. It's not that they have to do any analysis. Their brain just sees the pattern, right? And my question is, do you know, are there some people whose brain just automatically sees the pattern? So it's not like they have to think hard about it or anything else. It's just obvious to them. There's a set there instantly because of the way their brain works.
Yes, Hannah calls sets before she's seen them because she knows they're there. And she knows if she calls set in the time that it takes her to call set and get her hand down to where we're playing, she knows she'll spot it by the time her hand gets there.
So she just—
And I yell at her because I say, you called that before you saw it. And she said, oh, how do you know? I just know.
So is that something she practiced on, or is that just the way her mind works?
I think both. But
Okay.
I think her mind, I think this game was made with her brain in mind. I cannot imagine. So the set puzzle, you click the 3 cards that make a set. It says, great, you found a set. And then it used to be you had to hit the enter key to make the dialog box go away. So to find 6 sets, you had to click 3 times and enter 6 times. That's 18 clicks and 6 enters. Her best time was under 10 seconds.
Yeah,
she's good.
So then here's a related question. What procedure algorithm do you use then in order to find sets? Do you just take any 2 cards and quickly ask what would the 3rd one be, or how do you start off? Given 12 cards, how do you start looking for them?
I tend to try to look by attribute. So I'm first looking for set, collecting things together that are 1s or 2s or 3s, and then continue to add to that. That's the way I tend to do it. I think 12 is too many for you to pair them up and look for the 3rd card, figure the 3rd card out and look and still be finding sets.
How does your daughter do it? Do you know?
I'm sorry?
How does your daughter do it? What's her?
She and when I've been playing a lot and playing well, I've actually had the occasion happen that 3 cards jump up off the table and say, we're a set. And I go, oh yeah, you are. Thank you. I mean, I don't know what my brain is doing to find the set. They just pop. You play a lot and that can start to happen. Any other questions? Are there any in the dialogue thing, or? I don't know.
Are you still getting better at it?
Now I'm getting older, so I'm getting slower.
Okay.
That's what happens when you get old, is things get slower. I'm not as fast as I was, but I'm still pretty good. I'm still pretty good.
It must be maybe the number 2 champion in the world, or?
No, I think my older daughter's better than Hannah's the best. The older one's next, and here's Gary to say.
Yeah, I mean, as a case study, you can get better, and I think like anything else, but there's a limit when your brain does this. Everybody else's brain is finding sets. It's actually one of the problems with playing against Hannah is that if I see a set and she hasn't said set, then I think, oh wait, maybe it's not a set, because if it had been a set, she would have already found it. So you got that kind of game in your brain.
Yeah.
Have there been any generalizations of this to higher dimensions of sets with maybe more attributes, more higher number of cards that might correspond to geometries that have greater numbers of points in them?
So one of the things that's interesting is when you have people sort of thought about just adding another color, another color, another shape, another shading, and another number. It does, you do lose the 2 cards determine a set, because if you're doing just following the all the same or all different rule, it's not going to work. If whatever 2 you have, there's actually 2 different ways that the remaining 2 could pile up, could match up. However, Lauren Rose has come up with a game that she's called Even Quads. That's a set-like game with 4 cards in a set. And the Association for Women in Math is selling set quads decks in honor of their 50th anniversary. And on the reverse side, it's got women mathematicians. It's a lovely thing. I'm not sure they've finished it yet, but if you go to the Association of Women in Mathematics website, you can find that. Yeah, I mean, there are lots of people have asked a lot of questions. There's a projective version of set, and I've made a deck of my own, and that's in the book. So there are projective versions. There's a lot of very interesting things because it's geometry. Everybody loves geometry, don't they? Any other questions?
I think that's it. Well,
right.
Liz McMahon, thank you so much for your wonderful talk. And we'll all be off
Thank
to
you.
research
This was a lot of fun.
It is a lot of fun, and we're all going to be starting playing set games, I'm sure now.
I hope so. I hope so.
Okay.
And it is a great game to play with kids, but the fair warning, when you play with children, they internalize the rules quickly and then they crush you. I mean, every young person that I've played, the younger you learn, the better you get, and they really crush you.
Okay.
So you have to be humble. But
right.
It's a great game for kids, and that's what Hannah and I have done forever. Is we just ask questions, and that was what was the genesis of the book, was saying we've been asking these questions and answering them. I think there's enough here for a book.
Okay. Well,
and in fact, there's more than enough for a book. There could be a volume 2.
well, we'll look forward to both.
Thank you.
Thank you very much.